Welcome to the lecture on masonry testing. After watching lecture 6.1, you will understand how laboratory experiments and numerical simulation combined together can lead to a better understanding of the behavior of masonry during earthquakes. Experimental work is needed to determine the material properties and the structural behavior. But how can this be tested in practice? In this lecture we will consider three types of material testing: in-plane, out-of-plane and large-scale tests, and we will have a look at various examples from experience carried out in the Stevin laboratory of the TU Delft. Let's start with an animation. It is output from a numerical simulation. This example shows what can happen when masonry is loaded in plane. A horizontal force is applied at the top, while the bottom is kept fixed. The force applied to the masonry will result in a shear force in the masonry. However, due to the elongation over one of the two diagonals, principal tensile strains will occur. And these strains result in diagonal cracks in the masonry. As you can see, the direction of the cracks swaps as well, depending on the load direction. Now let's have a look at a real experiment. Here you can see a detail of a wall after testing it. It was loaded in plane by a horizontal force similar to the one shown in the animation. This part was an experiment at TU Delft during an experimental campaign for NAM. This masonry consists of calcium silicate bricks fixed with a traditional cement-based mortar. It is very similar to the type of masonry frequently used in Groninger houses. You can clearly recognize here the two diagonally shaped series of cracks going from both the top left to the lower right and from the top right to the lower left. If you examine one of the cracks in more detail, you can see that the head joint has opened while the bed joint is still connected. At the same time, however, a clear horizontal shift is visible between the bricks due to the sliding action. At some locations, as you can see, the mortar has disattached and it falls out. At other locations, the cracks have taken a shortcut directly through the cross-section of the bricks. The repeated cyclic movement has led to a concentration of vertical cracks, and this has caused severe damage to the masonry. Especially at the crossing point of the two diagonals, this is a behavior typical for seismic loads on masonry. A test on a large wall carried out in the Stevin lab, you can see clearly the diagonal cracks developing as described before. At some points the diagonals are even repeating on more than one position. You will recall from the previous lecture that masonry can also be loaded out of plane, for example due to seismic acceleration perpendicular to the wall. In this video we can see that the bricks have been sliding in the direction perpendicular to the wall. This wall was built from the same calcium silicate bricks as the one shown in the previous video. This animation from Diana shows the displacements of a wall loaded out of plane. At the four edges it is kept in place and in the middle it is moving back and forth. In the slide we can see a typical crack pattern that is the result of out-of-plane loading. You can recognize here an envelope shape that is the result of out-of-plane movement in the middle of the wall and fixation at all four edges. The material here is not calcium silicate but clay bricks. The out-of-plane loading was applied using airbags, automatically inflatable and deflatable on both sides of the wall. Now let's have a look at a series of bricks glued together with mortar. They will be loaded out of plane. In the next animation we will see a cross-section of these bricks. If we look closely to the stresses and strains during out-of-plane bending, we can see compression on top side of the image in dark blue and tension on the lower side of the image in yellow. Since we know that masonry is not very good in dealing with tension, we can now understand why cracks develop. Furthermore, this gives us a clue how to reinforce masonry against this type of cracking. In this experiment, carried out by the companies Oosterhoff Hollmann and Sealtech, the surface of the masonry is strengthened with a mesh of fiber-reinforced polymers. During loading the masonry out of plane, this mesh holds together the masonry at a stretched surface, and this prevents cracks from developing quickly, and it contributes to the ductility of the masonry. In other words, the strength is increased and the deflection before final failure is much larger than without. And this is an important notion during earthquakes, since it limits cracks. It reduces damage, but also in case of severe earthquakes, it increases the time available for evacuation. After testing single walls, it is also necessary to test full-scale structures. Here you can see the test of full-scale structure in calcium silicate brick masonry and concrete floors, resembling a house. This house is tested by applying quasi-static cyclic displacements on both concrete floors. This gives the same type of stresses and strains in the masonry as a real earthquake would. By doing it slowly, we can carefully follow the crack development and forces during the full test. For this, over 200 sensors have been attached to the house. All their formations and forces are registered in a computer system for later evaluation. This type of tests gives us a better understanding of the strength and the ductility of masonry structures under seismic loads. The outcomes can be used for two things: thinking about possible strengthening measures and further refining our computer models for prediction. To conclude this lecture, let's repeat what we have learned. By testing samples, we get a better understanding of how masonry responds to earthquakes, and this knowledge can be used to verify our computer models or to predict damage risk on other buildings. Full-scale tests give us insight into the exact cooperation between different parts of the masonry by in-plane and out-of-plane action. Also here, further verifications can be done using finite element models. Thank you for your attention.